Good morning, and thank you all for joining us. It's 10:15 a.m. here in New Orleans at the 243rd meeting of the American Astronomical Society. My name is Kerry Hensley, and I'm the AAS Deputy Press Officer. I'm joined today by Susanna Kohler, the AAS Press Officer, and Ben Cassess, the AAS Media Fellow. I'd like to quickly request that everyone silence your cell phones or anything else that might make noise and interrupt the proceedings. The previous day's webcast videos, press releases, and presenter slides have all been added to the press kit, and the press releases associated with this morning's presentations will be going up on Twitter, on the AAS website, and on the Slack channel before being added to the press kit later today. So be sure to look for those there. A brief overview of the ground rules in case this is your first AAS press conference. I'm going to give a brief introduction to our speakers. We'll then hear from our 5 speakers in order, and we won't pause for Q&A in between the presentations, and we request that you not clap in between the presentations, but hold your applause until the end. Then we'll have our Q&A session, and for those of you who are watching on Zoom, feel free to use that Q&A feature to queue up your questions. And for everyone on Zoom and in the room, please remember to identify yourself with your name and affiliation. So the subject of this morning's press conference is supernovae and stars, and also some neutral clouds in the Milky Way. Our speakers, first we're going to have Ping Chen from the Weizmann Institute of Science, speaking about a 12.4-day periodicity and a close binary system after supernova. Next, we'll have Estefania Padilla Gonzalez from UC Santa Barbara and Las Cumbres Observatory, speaking on rare insight into the origins of type 1a supernova progenitors from a double detonation. Oops, try not to lose any papers. Next, we'll have Mojgan Aghakhanloo from the University of Virginia, speaking on periodic eruptions of a supernova impostor. Following will be Alex G. from the University of Chicago, speaking about spectacular nucleosynthesis from early massive stars. And our final presenter this morning will be Jay Lockman from Green Bank Observatory, speaking about a new census of neutral clouds in the Milky Way's nuclear wind. So with that, I'll hand things over to our first presenter.
Okay, good morning, everyone. Thanks for being here. So my name is Ping Chen. I'm a postdoctoral fellow at Weizmann Institute of Science. And also thanks for this press office giving me this opportunity to talk to you about our recent work. So this work really is a result of collaborative efforts at Weizmann Institute and also within ZTF collaboration. I want to highlight 2 major collaborators. One is Professor Aghakhanloo, he's from Weizmann Institute, sitting in the audience. Also Professor Jesper Solomon from Stockholm University. I cannot list all the co-authors here, but their contribution to this work are essential. Okay. So before jumping to our discovery in this paper, I want to give some introduction to this background. So this is a very simplified a picture of latest stages of massive star evolution. So the massive star explode as supernova and produce neutron star and black hole. But the massive star explosion look very different if we take spectra at near peak light. Some spectra they have this strong hydrogen emission or absorption, and some they have pronounced helium. Some of them just do not have hydrogen or helium. So the reason for that is the amount of hydrogen or helium envelope of the projectile when this supernova happen. So to the most right, I show the onion-like structure of massive star. So you can see this in the outer layer, there is hydrogen and helium envelope. For those supernova, it doesn't have hydrogen or helium envelope. These are just, we call this type 1c supernova. So that for this type of supernova, when the supernova happen, the projectile star have already lost its outer envelope. So the reason for how this massive star lost this outer envelope is hotly debated. So It could be that the massive star has strong wind, it just blew away its envelope, or it's through a binary. The binary indexing can strip away outer envelope from a Progenitors star. Okay, another aspect of massive star explosion is that it could produce this most compact and enigmatic object in the universe, so neutron star or stellar mass black hole. But the direct link from the massive star explosion to the new compact object formation has been elusive. If I would give an example, it could be this crab pulsar. It's a neutron star at the center of a supernova remnant. So you can connect the neutron star to a supernova exploded around 1,000 years ago. But in our recent work, we built a link, directly from observing the supernova itself to the formation of a compact object. So this supernova is 2022 GLI. It was discovered by amateur astronomer. Soon after this discovery, it was classified as type 1c supernova. So this means that when this supernova happens, the Progenitors star has already lost its envelope, hydrogen and helium envelope. Physically, okay. One spectacular aspect of this supernova is we found this periodical undulation in the light curve. So here I saw the light curve observed in different filters. You can see there are also these zigzag-like undulations. As I mentioned earlier, this is a type 1c supernova, so we do not expect to see hydrogen in the ejecta. But in the late time, during the phase where we see this periodical undulation in the light curve, we detected hydrogen emission. And in the left panel, I saw the zoom-in view of the spectral sequence evolution around this H alpha region. And in the right panel, it's just the H alpha lines after subtracting the continuum. So more interestingly, we can see this the central wavelength of the H alpha. It's not a constant, so it's shifting. So this shifting is consistent with this having a 12.4 day period. So why we see these periodical signals in this supernova, both the undulations and also the H alpha emission. So there must be a clocking mechanism. Yeah. So we know that a binary system with fixed orbital period is a most natural mechanism to produce periodicity. So combine all this information, we get the following picture for this supernova. So the progenitor of the supernova, it's in a binary system. When the progenitor ages into red supergiant, it lost its envelope to its companion star, so it explodes as a type 1c supernova. During the explosion, it produces a compact object, and this newly formed compact object and its companion star, it remain bound in a binary system. So this binary orbit is an elliptical orbit with significant eccentricity. So that means during its orbit, so this compact object will approach and get away from its companion star. So every time this compact object is near the companion star, it will grab mass and form a crystal disk to power the supernova. Because this created material is from companion star, it's hydrogen rich. That's why we see this hydrogen emission. Also, this velocity shifting is also consistent with the compact object orbital motion in the binary system. So this is a brief summary. So we found the direct evidence for strip envelope supernova happening in a binary system. We built the link between supernova exploding and the formation of a compact object. We think this discovery have important implication for us to understanding binary evolution and also the formation of a double compact object formation. Okay. Thank you.
Hi, everyone. Thank you so much for being here. My name is Estefania, and I'm really excited to present some of my work that has recently been accepted for publication. It's a rare type 1a supernova coming from a double detonation. So supernova type 1a are like standard candles with predictive luminosity. The same way that you look at distant street lights appear dimmer, Supernova type 1a also look dimmer with the distance, but because we know their luminosity, we can work out their distances. And this is really important because it led to the discovery that the universe is actually accelerating, and it won a Nobel Prize. So white dwarfs, which are the progenitor stars of supernova type 1a, alone cannot explode. They need a triggering mechanism. And so they actually need to be in a binary system with a white dwarf in the sun that can donate some of the mass to the white dwarf. And when it reaches a mass limit or the right temperatures and pressure, it can cause an explosion. However, even though type 1a supernovae have been studied extensively, their explosion mechanism still remains elusive. So by comparing the supernovae light curves to theory, we can predict the ejecta masses. However, from studies, they have found that up to 50% of type 1a supernovae have ejecta masses less than the Chandrasekhar mass limit, which this means that a lot of these type 1a supernova come from smaller white dwarfs. But this idea was not widely accepted for a long time because simulations of the sub-Chandrasekhar mass explosions did not really match the observations that we see for normal type 1a. So the question is, how can we actually get the smaller white dwarfs to explode? So this scenario has been explored since the 80s. Well, the answer is that we would simply need more mass. So you have a smaller white dwarf, and you have it in a binary system. You donate some of the mass to the white dwarf, and then what ends up happening is that you end up having this thick helium shell around the white dwarf, and the helium shell actually begins to ignite. And you can see here in this video that you have the ignition happening in the shell. It converges at some point, and it sends a shock wave, compressing everything in the core, and then causes a secondary explosion. However, observables can look very different depending on the thickness of the helium shell. So here you have a plot. Here at the top, you have more of the thinner helium scenario, and then the bottom is a thicker helium scenario with different elements that have been synthesized. And the main takeaway of this plot is to see that for the thinner helium shell, you synthesize a lot more of the intermediate mass elements, which are more like silicon and calcium. And at the bottom, you have thicker elements such as nickel and chromium. So now let's look at the data that we found. So here we have in the black supernova 22JOJ, and then we also have the normal type 1a supernova in the gray. At the very top, we have the earliest data that we have, and then as it evolves at the bottom at some later time. The main thing to see here at the top is that there's a big discrepancy in supernova 22JOJ and the normal type 1a supernova in this area. There's some sort of suppression happening with 22JOJ. And as you can see in the red, the model also predicts this, and double detonations can explain this because when you have the helium ignition, it creates a lot of the helium ashes that can absorb a lot of the blue light. And so that's why you see this suppression. But the interesting part is that as it evolves, as you can see here at the bottom, it looks more like a normal type 1a in both scenarios, in the models and in the data. And so now we have this. If we also look at the color evolution over time, if you go in the top in the y-axis is redder color. So here you have a scenario of the normal type 1a 11 Fe. As you can see, the color evolution is for the most part blue. But if you compare it with supernova 22JOJ, you can see at the very early phases it's a lot redder, which is something, and as it starts to evolve, it looks more like a type 1a here at these later times. But the models, interestingly enough, also predict that for these double detonations with the thinner helium shell, you have this reddening at the early phases, and as it starts to evolve, it also looks like a normal type 1a. And what I really like to emphasize is that if we didn't have this early data, we would probably just think that this is a normal type 1a. And this happens within days. So here we have a table of all the double detonations that we've discovered. So this encompasses less than 1% of all type 1a supernovae. And we have the thick helium shell at the top and the thin helium shell at the bottom. And what I really like to emphasize is that even though we only have a few scenarios for the thin helium shell, what stands out about 22JOJ is that this is the first, one of the best evidence that we have of double detonation with the thin helium shell, because for a long time, it was this scenario of a double detonation wasn't really believed. And so now people are starting to be convinced that double detonations with the thin helium shell can actually be a triggering mechanism for a lot of these type 1As. Because before we had the thick helium case, and as I mentioned, the elements are so different that it looks very different for a type than a normal type 1A. And so to conclude, the supernova 22JOJ is the best evidence that we have for a thin helium shell scenario. And from studies, up to 50% of type 1A come from smaller white dwarfs. And since in the thin helium shell case, this appears hours, if not after days after explosion. So it could be the case that we missed a lot of these double detonations. These double detonations may be a lot more prevalent in nature than we previously thought, and they can perhaps explain half, if not more, of all type 1A supernovae. Thank you.
Hi, my name is Mojgan Aghakhanloo. I'm a Vita Origin Fellow at University of Virginia, and today I'm going to talk about periodic eruptions of the supernova imposter supernova 2000 CH. In the right side, you can see supernova 2000 CH during one of its eruptions captured using the Kuiper telescope. And today I'm going to talk about what is causing these eruptions. This work has been done while I was a postdoc at University of Arizona, working with Professor Nathan Smith. So supernova imposters, they are evolved massive stars that they have undergone non-terminal eruptions. Their non-terminal eruptions are usually associated with they are usually misclassified as supernova explosions. But since the star survives the eruption, they are labeled as supernova imposters. Their eruptions are associated with luminous blue variable or LBV phase of massive stars. LBV phase is a post-main sequence phase of massive stars when the massive star is unstable and variable. In the right side, you can see Aghakhanloo, which is the famous galactic luminous blue variable. But today, I'm going to talk about an extra galactic supernova imposter, supernova 2000 CH. Here you see the light curve of supernova 2000 CH from 1994 to 2010. Supernova 2000 CH experienced its first eruption in 2000, and then later in 2009 and 10 experienced 3 more eruptions documented by Pastorello 2010. Using the new observations, we found that supernova 2000 CH experienced 3 more eruptions between 2004 and 2007. We also studied its light curve from 2010 to 2023, and we found that it experienced at least 16 more eruptions in past 1 decade. So supernova 2000 CH since 2000 experienced in total 23 eruptions. Here you see the zoomed in version of its 3 recent eruptions. And as you can see, in each eruption, there's a clear rise and fall, but each eruption looks very different than the other one. And later I'm going to talk why they look different. Our investigations shows that these eruptions, they do repeat with a period of around 200 days. Here you see the light curve that I showed earlier. In the left side, we have the light curve from 1994 to 2010. In the right side, we have the light curve from 2010 to 2023. And the red vertical dashed lines shows the estimated time of the eruptions using the detected period of around 200 days. And as you can see, majority of them, they align with the estimated period. So since these eruptions are periodic, we propose that this is an eccentric binary system And these eruptions are caused by interaction between two stars. And the primary star in this eccentric binary system is a variable unstable star like a luminous blue variable. In part A of this figure, you see the primary star when it's during its dormant state. So when two stars are close to each other, the interaction between two stars is weak or even absent. In part B, you see the primary star during its outburst state when it has a larger radius, is losing a lot of mass. So when two stars are close to each other, the interaction between two stars is much stronger. So because of the intrinsic variability of the primary star, each eruption looks different than the other one. This is a target of great interest because these eruptions, they look very similar to eruptions of Aghakhanloo leading to its giant eruption. They also look very similar to the pre-supernova eruptions of supernova 2009 IP. So we highly encourage to monitor supernova 2000 CH because it may merge or it may become a supernova. So in summary, using all the new observations, we showed that supernova 2000 CH experienced at least 23 eruptions since 2000. In the right side, you see supernova 2000 CH during the 16th outburst captured using the Kuiper telescope. Our investigation shows that these eruptions, they do repeat with a period of around 200 days. And we propose that these eruptions are caused by interaction between two stars in an eccentric binary system where the primary star is an unstable variable star. And given the detected period, we can predict the upcoming eruptions of supernova 2000 CH. And the next one is going to be March of this year. And at the end, I would like to highlight that if you are interested in more details, you can access the published paper using the QR code. Thank you.
Can everyone hear me? Some nods. Okay. Thank you all for being here today. I'm very excited to tell you about some new observations taken as part of the Sloan Digital Sky Survey 5 survey that pushes our understanding of how the first massive stars in the universe may end their lives. This is a work that was recently accepted to the Astrophysical Journal Letters. It's now available on arXiv at that QR code link. There are 42 co-authors on this. I wanted to highlight 3 of the juniors people who worked on this. Sanjana Curtis led the nucleosynthesis interpretation. Nicholas Storm did a lot of the work on the chemical abundance analysis, and Vedant Chandra was crucial for actually identifying this object of interest. The image that you see over here is an artist's rendition showing what we are actually doing, which was we're learning about an ancient supernova by studying the chemical composition of stars observed in our Milky Way galaxy today. And so I'll explain this a little bit more later. I was told to get straight to the point, so here's a summary of what I'm about to talk about. So what we have done is we've discovered a new star inside of the Sloan Digital Sky Survey that displays an absolutely spectacular chemical composition that we've never seen before. This traces the output of a unique supernova that exploded early in the universe of order 13 billion years ago. We think this is interesting because it appears to be a supernova of a star that we think shouldn't have gone supernova. It's so massive, it should have just turned straight to a black hole. But we're not totally sure because we're actually right at the edge of what our current models are predicting for basically what massive stars should do. There's a list of people to contact on here, as well as a QR code for the paper as well. So that was a lot of different things that I just said. If you don't remember, if you don't want to remember anything else, you can remember that what we studied was the Barbenheimer star, because this is what happens when you study spectacular nucleosynthesis during the summer of 2023. So taking a step back a little bit, this project is part of the Sloan Digital Sky Survey, and in particular, the part of it that's called the Milky Way Mapper. What we are doing is basically lawn mowing through the entire sky, taking spectra of every star that we can get our hands on. The main thing that allows us to do this is we put on robots onto some of our telescopes, and that allows us to take a lot of spectra, a lot more than before. This is going great. We're taking lots of data, and right now we're looking through the early data, looking for sort of rare gems that might tell us something interesting from individual objects. And indeed, we found a rare gem. This star, I'm going to call it just for short J0931 because telephone numbers. And this is SDSS actually flagged this star because it had an unusually low magnesium abundance for its given metallicity. And then so we decided last year to follow it up with the Magellan telescopes at Chile, getting a high resolution spectrum. And this is the sort of data that where you take it at the telescope, you look at it and you just say, oh, wow. And then you send out an email to everyone saying, we found a spectacular star, literally. So what you see on the right figure over there is our star spectrum is shown in black, and two normal stars are shown in purple and blue. And I've labeled the basically where elements show up in the star spectrum. If the line is weaker, that means there's less of that element. And if the line is stronger, that means there's more of that element. And so what you can see just looking at the black compared to the other ones is there's a tiny amount of sodium as well as a tiny amount of barium and titanium, but a very large amount of strontium and manganese. This is a never before seen composition and one of the most extreme compositions we've ever observed in a star ever. So how do you actually get a star to look this weird? We think this is due to an ancient supernova that basically created a unique distribution of elements. The idea is illustrated here. There is some early supernova that explodes. It creates a strange distribution of heavy elements. Those make their way and imprint themselves upon the next generation of stars that form. Then over the next 13 billion years, the massive stars that were born there die out, but the low mass ones actually survive. And so what we do now is we dig through our Milky Way, find these old low mass stars with strange chemical compositions, and therefore indirectly learn about that early supernova. And what you can see here is that this is what the artist illustration is depicting. So this Barbenheimer star is the early star that went supernova, producing a spectacular distribution of elements. But we actually observe it in a low mass star in our Milky Way today. So what type of supernova could have produced this particular distribution of elements? What we know for sure is that it seems to have to be a massive star whose initial mass was over 50 solar masses. And our best fit to this is actually an 80 solar mass star that explodes with something like 22 times the energy of a normal supernova. We get this basically by looking at how much iron is inside of the star and the distribution of elements that's less than calcium. But actually no model in our, we looked through 40,000 different models, nothing in the literature appears to actually explain the entire abundance pattern. In particular, the distribution of elements near iron is something that no one seems to be able to explain. And so what we think this means is we've basically reached the limit of what our models are able to predict. We don't know how to produce chemical patterns like this when we explode a supernova. But what's interesting about this is if you take it at face value, we have an 80 solar mass star that exploded. This is a star that probably shouldn't have exploded. The image you see here is from the Chandra Observatory's beautiful depiction of stellar evolution. I've sort of labeled what we think stars of different masses should do when they die. And what you see in that sort of second from the top row is that if you have a star that's sort of from 40 to 140 solar masses at birth, when it dies, it should pretty much just collapse straight to a black hole without an explosion. On the other hand, we seem to have seen a star at 80 solar masses smack dab in that range that appears to explode and also produce a huge distribution of elements that we haven't seen before. So now we think maybe these sort of stars might explode. So in summary, this is spectacular nucleosynthesis in early massive stars. We found a star in Sloan Digital Sky Survey with a spectacular composition that records the explosion of an ancient supernova. It's probably a supernova from a very massive star that should have turned into a black hole, but we're really at the limits of what we know about how massive stars explode. I did manage to put the link to our press release down here at the bottom, as well as contact emails for people who you can reach out to about this particular thing. And if nothing else, it's the Barbenheimer star. So thank you very much.
Thanks. I'm Jay Lockman from the Green Bank Observatory. Most of me is here except my voice, which seems to have been left in boarding area C21 at Dulles Airport, where I spent the morning of Monday sleeping on the bench there. Most large galaxies, and this is not the Milky Way, have explosions in their nucleus caused either by bursts of supernova, which we've heard about so eloquently today, or the black hole that drive these enormous winds into intergalactic space. This is a nearby one, and it shows an example of the phenomenon. Now, here's an artist's conception, but what's across here is an actual photograph of the Milky Way, and you can see all these dark clouds here, these dark patches. That actually prevents us from seeing anything like this in the center of the Milky Way in the optical. But we've had data over the past 20 years or so that indicates a similar phenomena is going on in the nucleus of the Milky Way. And this is important because if we can study it up close, it gives us a template for something we can apply to all large galaxies. The magnitude of this phenomenon is really spectacular. Material can be recirculated through a galaxy. In some cases, the explosions are so great, it could even strip all interstellar matter from a galaxy, quenching future star formation. This artist's conception shows what we've been doing with the Green Bank telescope. We've been mapping out, discovering cold hydrogen clouds that are entrained in the hot wind from the nucleus of the Milky Way. The wind is more than 1 million degrees hot and is traveling at thousands of kilometers a second and has caught up these hydrogen clouds that we are able to detect through the radio emission in the hydrogen line. It's kind of like a snowblower, all right? And it's kind of like a leaf blower. Neither of them are completely adequate. The snowblower is great because it's a collimated sense of this cold material being thrust up from below that kind of shreds as it goes up. That's a really good image. But there's no central whirling thing. In fact, it's like a leaf blower in that it is a wind that you cannot observe directly, but you see its interaction in the leaves that are blown. But unlike a leaf blower, it's collimated. And so it's some combination of a intergalactic snow leaf blower. Here's how we think about it. We think of two collimated cones coming out above and below the Milky Way, and the red indicates velocities away from us, the blue toward us. So you see, if we look in a given direction, the near side should be coming toward us, the far side should be going away from us. These things are huge. We should see things at different stages of evolution as a function of velocity. And so we can take our clouds and then locate them in three-dimensional space. And that's what we have been doing now, painstakingly making observations with the Green Bank telescope and collecting this bunch of clouds. And we now know that we see more than 300 of these hydrogen clouds. It's a biconical outflow, 1/10 of a solar mass per year, but it's been going on, we believe, for at least 10 million years. So it's taken 1 million solar masses of hydrogen and sent it up into intergalactic space. The velocities are very high. At a conservative limit, we see things at 500 kilometers a second, and it could be twice that. And, you know, we get the projection across the line of sight, and so we really don't know how that goes. It could be much more than that. This is approaching the escape velocity of the Milky Way. Now, one of these clouds is unlikely to actually escape. It has a lot more matter to plow through, just like the snowblowers. Gravity is pulling it back down, but we're dealing with certainly the ability to launch things in the Milky Way and have them land at other places and kind of stir up the disk. We're seeing evolution of the clouds, as you might expect, as they're blown on by this hot wind. They get shredded, they get mixed in with the hot wind. In fact, they might be capable of actually quenching the wind at some distance from the galactic center. They also contain molecules, and this is so astonishing, no one would have ever predicted it. These are clouds that do not have the density and the dust to shield them from ultraviolet radiation, and yet the first two clouds that were observed with the APEX telescope in Chile, both of them showed carbon monoxide emission, implying that half of the mass was in molecular and half of atomic. We now have something like 10 clouds detected with a molecular component. Again, they show evidence of evolution, of cloud shredding. This must have been material that was dredged up from right near the center of the Milky Way and is now evolving as it goes upward. We now know enough about our model that we can identify areas that don't have hydrogen, neutral gas, and in fact, we see through some a very few observations with Hubble telescope that area is ionized. And so we're seeing regions in the expanding cone where the ultraviolet radiation from down low is now ionizing this. We're putting this all together into an amazing picture, learning more daily as we go about this really amazing phenomena that's involved telescopes now around the world and a lot of different wavelengths. It's really cool. Thank you.
All right, with that, we can go ahead and one moment. All right, with that, we can go ahead and get started with our Q&A. So if you're watching on Zoom, please queue up your questions using the Q&A box and remember to tell us who you are and who you're affiliated with. And we'll have someone in the room bring around a microphone. Yes, okay. Susanna will bring you around a microphone if you're in the room.
I'm Robert Schilling, freelance from the Netherlands. I have a question for Ping and a question for Mojgan. From the binary orbital period, can we say something about the mass of the companion and the mass of the compact objects? Is that something you can say? And for you, I was wondering, is there a relation between, for Mojgan, is there a relation between the system that you describe and the system that Ping said? Could one be the progenitor of the other?
So for the mass, so in general, the mass of the system is going to be around 40 to 60 solar mass. But
Okay, so now for this system of this supernova, the 12.40 is over. So now we have the information of the period 12.40. So to get the mass, the dynamical mass of this system, we need more information. So because this, we have some information on the eccentricity, but that's it. We have only the really accurate information on period. Besides that, we do not have much information to derive accurate mass for both the compact object and the companion star.
Can you repeat your question, like between the progenitors and?
I was wondering if the system you described could be something like a progenitor to the system that Ping described. Would it end up in a similar way?
So the system that I describe is a progenitor of interacting supernova. So it's mainly progenitor of supernova type 2Ns.
I'm Martin Ratcliffe of Evans and Sutherland Planetariums. This is for Mojgan as well. In NGC 3432, your galaxy, how in the paper online it says you were predicting 2023, but you orally said 2024. What is your prediction for that peak, and do you know what the peak brightness is for all the amateur astronomers around who might go photograph it?
Yes. So in the paper, we studied the light curve till the end of 2022. So we mentioned the outbursts, the eruptions in 2023. But today, because we are already in 2024, I said 2024, so we can observe it. So yes, we have a lot of data from Kuiper, Super Lotus, ZTF, Atlas for 2023. But we are going to analyze those and decide whether there was any eruption during the predicted times in the upcoming papers. We don't want to conclude anything before like having all the data together and look at the peaks.
Do you know what the peak brightness is or has been?
Yes, the peak brightness is usually around 17 apparent magnitude.
Okay.
Yes.
Within range of a 16-inch telescope.
Yes.
Camille Carlisle, Skying Telescope Magazine. My question is for Alex. Could you clarify what makes you think it's about 80 solar masses? And you probably know where I'm going with this with connections to LIGO and how big the mass of the black hole might be.
Yeah, that's a great question. So there's two pieces of evidence in favor of the 80 solar masses. One is basically it's only stars that are that massive that actually end up producing enough iron to make up what we see inside of the star. And the other one is when you look at the distribution of what's predicted for 80 solar mass stars compared to every other mass star that people have done these calculations for, that's sort of what gets you the best answer, although there's a range of things kind of around 80-ish. And then in terms of what that would mean for black hole masses that are left over. So normally you would expect if you start with an 80 solar mass star and it doesn't lose mass, you end up with an 80 solar mass black hole. In this case, if you expel a huge amount of mass in the supernova explosion, you'll end up with a less massive black hole. We can't say exactly how much mass was produced. That's very model dependent, but it would be less than 80.
I have a question for Estefania. I was wondering, oh, sorry. I'm Ethan Siegel from Starts with a Bang. Estefania, I wanted to know, you listed the known double detonation events and then mentioned that these known double detonation events represent fewer than 1% of all the known type 1A events. And then you talked about how up to 50% or even more of the supernovae may inevitably be due to double detonation. And I've heard Chen say that as well. So I'm curious if there are any indicators, either yay or nay, in all of the other sub-Chandrasekhar type 1As that you've seen that have the early time series data. When you have the early time series data for these other type 1A supernovae, are they consistent with what you showed us is the way to tell, is this probably double detonation or not? What do you see when you look at that?
Depending on the thickness of the helium shell, it can determine how long this reddening will last. So for example, like in 2018 AOZ, it was another double detonation with the thin helium shell, but the effect only lasted hours. For my case, it was a few days. So it really depends on the thickness of the helium shell. And so that's why it's very critical to have these like really early observations. But for the 50% was, yeah, mainly because I mean, most of the white dwarfs that we see are peak like around 0.6 solar mass white dwarf. And so because of that, we know that, and from studies, they have shown that the masses of the ejecta are up to 50% or less than the Chandrasekhar mass limit. So we know that there has to be a lot more of this sub-Chandrasekhar mass white causing the explosion.
It's Camille again. This question is for Jay. Could you clarify the connection or lack of connection to the Fermi bubbles?
Yes, that the Fermi bubbles are these very large regions visible in gamma rays extending 20 or 30 degrees above and below the galactic plane. In fact, when we are modeling the kinematics of the hydrogen clouds, we assume that they lie within the boundaries of the Fermi bubbles. And so it is somehow connected to that, but the connection is certainly not clear.
I also have a question for Jay. What is the relation between these clouds and the high velocity hydrogen clouds that we've seen? Do we know for sure that your clouds reach escape velocity, or could they be related to the infalling material?
Yeah, I think they are all high velocity clouds, but I think the classic high velocity clouds are infalling and are not necessarily connected to these events in the nucleus of the galaxy.
Hi, Ethan Siegel from Starts with a Bang again. This question is for Alex. Alex, I understand from what you've shown of the elemental abundances in this star that it's unlikely to have arisen from a well-mixed ISM that has contributions from lots of different things, that we're probably getting extreme contribution from one event that was well differentiated. But I wanted to ask, you talked about our expectations for, oh, this type of mass star with this metallicity should lead to this type of, should it lead to direct collapse? Should it lead to a supernova? I would want to ask you, why should we believe what any theorist says about direct collapse and when it should occur, given that the first star we ever saw directly collapse was only 25 solar masses, and that's not supposed to happen. And LIGO has seen pre-merger black holes of over 100 solar masses, and that's not supposed to happen. So, and also, why should we even believe that mass and metallicity are the only determiners of whether you get supernova or black hole? So, you mentioned it, but can you be honest with me about this?
Yeah. So why should we believe theorists ever? Is that what? So I think that's a really good question, and in some sense, that's one of the most exciting aspects of this. Is it gives us a really nice target system to begin understanding some of these questions, right? So, for instance, one example of a thing which I didn't talk about is, one of the things that would be great is if you started with a high mass star, it started at 80 and then somehow it lost a whole bunch of mass, but it has to be metal poor. So how do you do that? Well, if it's in a binary, it can interact and lose a whole bunch of mass, and maybe you end up with something like that. Or alternatively, maybe it's extremely rapidly rotating and it has to have some sort of jet process that is involved and produces this very weird distribution of iron peak elements. The theorists, I hope, are going to have a playground just explaining how you produce a system like this. Is that a satisfactory answer? Because I don't want to impugn my reputation too much.
Thank you for telling me what you think. I appreciate it.
Thank you.
Just a quick response in defense of theorists. Juno Kohlmeyer, SDSS5 director and CEDA director. The point is that you're not supposed to believe, you're supposed to understand. And the point of doing big surveys is to challenge our understanding by finding things that are outside of what our current calculations do. And so this is really a synergy between theory and observation to yield deeper understanding. And it's exactly these types of, falsifications that we're seeking in big surveys and as theorists who actually want to understand deeper about the universe.
We have questions here in the room. I have a few if people want to think a little bit longer. Or Camille, you can go first.
I'll keep talking. It's Camille, Sky and Tell again. This question is for Mojgan. Did I say that right? Following up on a previous question, if there are highly equipped amateur astronomers who would like to be involved, do you have some sort of campaign or way that they can reach out, or what would you like?
Well, they are already doing it. Like in the paper, even there is one that amateur astronomer Etiaki, if I hope pronounce his name right. One of the outbursts is coming from amateur astronomer. There is a website, I think by Rochester University, that they compile all the discoveries for supernova imposters. So whenever we are looking at the light curves, we get the data from amateur astronomers too.
Okay.
Yeah.
So if for the upcoming March event, if anyone wanted to be involved, what would they do?
Usually, because this is a famous supernova imposters, they usually monitor it, continuously monitor it. And yeah, the paper is already published, so that we have the dates that when we should monitor it. So, but in general, I should also mention that it's continuously getting monitored by ZTF, ATLAS, and by the telescopes at University of Arizona, Kuiper, Super Lotus, and also Kate telescope. We observe it during the times that we think should experience an eruption.
So there's not necessarily a specific campaign through
No.
EAVSO or something.
No, but that actually, it was recommended to me a couple of days ago. So I think I'm going to submit
Okay.
for this target. And also there's another target. I wasn't aware that I can just submit my targets for AVS. But yes, we are going to do that.
Thank you.
Do you have any questions online? Okay, well then it's my floor. For Estefania, is there a difference in the detonation cause or mechanism for these thin shell detonations or the thick shell? I guess my underlying question is, why are some of the shells making it to a greater thickness if they have the same detonation mechanism?
Yeah, this has to be with the mass of the white dwarf. So if you have like a little bit more massive white dwarf, like you only need like more of a thinner shell to like. Yeah, so for the thicker helium shell, we're seeing that the masses of the white dwarfs are like lower. So you would have like around like 0.7, 0.8 solar masses, but then so you would have like a thicker helium shell, but you can also get a double detonation with the thin helium shell if the white dwarf mass is like a little bit more massive than that, if it were to be like somewhere like 1 solar mass. And so then you wouldn't need as much.
Great, thank you. And for Alex, knowing what we do about this star's position and hopefully its kinematics, are there any hopes of finding this star's siblings that were enriched by the same supernova?
Siblings of the same star. I really hope so. So far we have not been able to find it. As soon as we find one, we'll know immediately because it should have the same signature. And we do know its kinematics, and that's one of the reasons we're running these large surveys is to find stellar siblings like that. So we tried really hard, did not succeed yet. Hopefully it's coming.
Cool, that's definitely something to look forward to. All right, do we have any last questions here in the room? Yes, Ethan.
Hi, this is Ethan again. Estefania, I'm coming back to you. I want to ask you, one suggested mechanism for type 1As is from the mergers of two white dwarf stars. If this is responsible for a fraction of the sub-Chandrasekhar mass events that you see, could that also be consistent with what you're observing, what you're looking at, rather than just a double detonation of a single white dwarf? Could that be triggered by a companion? And can we ever get a companion where both white dwarfs go supernova from colliding with each other?
Yeah, so you can still get a double detonation from a double degenerate. So instead of being dynamically stable when you're like accreting mass, it would be unstable, but that can still trigger the helium shell to detonate, and then they would merge. So that would be for the double degenerate case. But you can also have like the single degenerate case where like the mass that has been donated is stable, that they wouldn't merge with each other. So you can still have both scenarios.
All right, any last questions here in the room? If not, I think we can go ahead and finish this session. A big thank you to the PIOs who helped to prepare press releases for this session, and to our sponsor, USRA. We sincerely hope that you'll join us this afternoon in this room at 2:15 p.m. for another press conference on stars, disks, and exoplanets. And with that, let's give a round of applause to all our presenters.